Thank you. Good morning, everyone. Ever since my school days, I was an ardent lover of nature and environment. So I used to be a big nature lover. But then the problem is I was also interested in technology and engineering. And for my university, I chose mechanical engineering for my undergrad. So this created kind of a conflict inside me because traditionally the notion is that engineering and technology is seen as the prime cause for destroying nature. A lot of the havoc created in the environment can be traced back to technological roots, right? So this conflict was there in me. And then for my PhD, I did aerospace engineering. I did defense related, my PhD topic was related to defense in aircraft. So the conflict grew. So, but then later on, I realized that fortunately or unfortunately, a lot of the problems that we face are because of technological problems, right? It can be rooted back to technology. But then the solutions also lie there. If you lose your keys in this building, there's no point in going to the next building and searching. You have to find it here. You can only find it here, right? So I realized that with technology, you can solve or at least mitigate the problems and the pressure that we put on the environment. So this talk that I'm going to give today is an example of how I reduced the conflict, my inner conflict, through my first job. So it was an energy-saving technology in the refrigeration industry, and I would love to share my experience regarding that with you today. A number of technologies have become indispensable for us today, isn't it? I don't just mean Facebook and Instagram, but then if we observe our daily lives, we use a wide spectrum of technologies, starting from our smartphone, automotive, internet, communications, everything. But one technology that works in the background all the time and is not as conspicuous as the others is the refrigeration technology. If I ask all of you to name one device in your house that works 24/7, 365 days a year, I think the most common answer would be your refrigerator. It works very hard, all the time, non-stop, right? So that's the case in the big global scale as well. We use this technology so extensively that it is responsible for 17% of global electricity consumption. On an average, a human being consumes 440 units of electric energy per year for just refrigeration and air conditioning. Even right now, we are using the technology to air condition this space, isn't it? So the thing is, if we make a small, efficient, energy-efficient technology in this, it can make a profound impact on the environment, right? It will have a cascading effect, and it can make a huge impact on the pressure that we put on the environment. On the commercial side of things, for a number of products like food and pharmaceuticals, these products have to be stored and transported in temperature-controlled supply chains called as the cold chain. Let's take the example of the milk that we consume every day. Okay? Right from the time it is bottled, it has to be stored in what is called as cold storage room or walk-in freezers in the dairy farms. And then it has to be transported in refrigerated vehicles, and then it reaches your supermarkets and shops, and then again it is stored in these cold rooms. And then it is displayed in this what is called as the chiller cabinets. And then you buy the milk, you bring it home and store it in your refrigerator. So this is the journey of the milk, just one product that you consume, and it goes through this cold chain. So numerous products, copious amounts of products journey through this cold chain. And this cold chain is so extensive and widespread that it is responsible for 3% of global greenhouse gas emissions. Right? That's a lot, actually. And this is through direct and indirect means. So this is one industry where energy-saving technologies and energy-efficient practices can make a profound impact. I think you all know the example of Montreal Protocol. During the late 80s, 1980s, the CFCs were starting to be phased out throughout the world. Yeah? And one of the main consumer of the CFC was the refrigeration industry. Right? So this is an important industry which puts a lot of pressure on the environment, and energy-saving technologies are quite vital for this one. A vast majority, now to a bit of high school physics, if you would excuse me. A vast majority of these refrigeration systems work on what is called as the vapor compression cycle. So basically, a fluid called as refrigerant is cycled through 4 basic components: the evaporator, the compressor, the condenser, and the expansion valve. So what happens, the evaporator will be staying inside the freezer space. So this is the freezer, that box is the space that you want to refrigerate, and the evaporator is usually is always inside the freezer. So now the refrigerant boils inside the evaporator, and when it boils, it absorbs energy from the freezer's cabin space. It absorbs energy and thus cools it down. If you ask the boiling point of water to someone, I'm sure the answer would be a very confident 100 degrees centigrade, right? But that is only a partial answer, because water, pure water, boils at 100 degrees centigrade at 1 atmosphere pressure. If you want to boil at lesser than that, you just have to reduce the surrounding pressure. And if you increase the surrounding pressure, it boils more than 100 degrees. So that phenomenon is put to dramatic use in a refrigeration system. So let's say, for example, you want to maintain a freezer at minus 20 degrees centigrade, and the ambient temperature is 30 degrees centigrade. So what you do is, you reduce the pressure of the refrigerant so low that its boiling point is reduced below minus 20 degrees centigrade, right? So it boils and becomes vapor, and then goes as vapor to the compressor. The compressor recompresses it now to such a high pressure that it starts condensing at temperatures higher than 30 degrees centigrade. So the condensation is the heat rejection process. It rejects the heat to the ambience and becomes liquid again. And then that liquid is circulated through the expansion valve, and the pressure drops happens across the expansion valve. So this is the cycle, basic cycle, right? So the evaporator would be our point of discussion today. I'm sure people above 30 years old are familiar with this situation in your freezers, right? I have faced it quite a lot of time. But nowadays in modern refrigerators, you don't see it a lot, because they come with what is called as the auto defrost technology, or a frost-free technology. This is the problem we are trying to solve, right? And it's an annoying problem. Okay, it happens because this evaporator surface is always at sub-zero temperature, less than 0. And there is moisture and water vapor in the air, in the freezer space. So when it comes in contact with the evaporator, it desublimes into frost. It becomes frost or ice. And that ice gets deposited on the evaporator surface, and this keeps on accumulating with time. If this is the situation that can happen to a home freezer, imagine what would happen to a big commercial walk-in freezer. A walk-in freezer can be very big, actually. It can be, I have been to freezer which are half the size of this hall. Okay, you can play cricket inside that. It's huge, huge, and all the stocks are stored inside that, right? So this frosting problem causes many issues to the evaporator and the operation of the refrigeration system. So that is the evaporator, which is placed in a walk-in freezer, right? So the evaporators, most of the evaporators, they are basically heat exchangers, and they are of what is called as the fin and coil type heat exchanger. So basically, the refrigerant flows through copper pipes like this, and then they are surrounded by aluminum fins to enhance the heat transfer area, right? And these fans blow air through this setup. So when the air is blowing through it, it gives out the heat to the evaporator and cools it down. So that's how the heat transfer happens. But when this frost is getting accumulated, all the air passageways get blocked like this. You cannot imagine any air passing out of such a situation, right? And the second problem is that this frost has some pockets of air inside it. And air is a bad conductor of heat, right? So when this frost is growing on this evaporator surface, it kind of creates an insulating layer over this evaporator. So combine these two effects, the evaporator does not do a good job of cooling the room down. And the refrigeration system fails without much delay, right? In hours, such a frosted evaporator, if it's not removing the heat, what happens is the temperature of the freezer will rise gradually, and it will become ambient temperature, and all the products inside that will perish. So in supermarkets and in a lot of other warehouses, the the frozen food is supposed to be kept at minus 18 degrees C, right? And if the temperature is rising, the food quality would be affected. You know the frustration of our milk getting sour if the refrigeration doesn't get work properly or the power goes off, right? The similar situation can happen, but this time the losses are huge, right? So there is a necessity to remove this frost periodically from huge freezers, and that is what is called as defrost, right? So now the burning question here, or in this particular situation, the freezing question is, how do we remove the frost? Yeah? But unfortunately, the method that is used in a vast majority of refrigeration systems to remove the frost is quite counterintuitive. Okay? You raise the temperature of the evaporator, right, above 0, and then the frost will melt into water, and that melted water will be drained off through a drain tray, right? That is the method, basic principle that has to be used. But the technical thing lies in how you supply that heat. You would be surprised that a vast majority of freezers, they use what is known as the electric resistance heating method, or the electric defrost as it is called. So they would place these electric resistance heaters, and it would be mounted on the evaporators at the 4 corners, and they would heat up this rod, right? Once it heats up the rod, it will transfer the heat to the evaporator coil, and slowly it starts getting above 0, and it will melt off the frost. So like you can see, the problem with this is that you are supplying enormous amount of energy to raise the temperature, because when you have ice and if you want to melt it, you have to supply the latent, what is called as the latent heat, which is a huge significant amount of energy to it, right? And then you are supplying external energy. And the second problem is that you have the defrost resistance heaters on the side. When it is heated, it's not just giving heat just to the evaporator. It is giving heat outside to the freezer also, right? So the freezer temperature also rises during the defrost, right? And during the next refrigeration cycle, you again have to, so this defrost is done 4 or 5 times a day, and each defrost can last up to 45 minutes, okay? So the reason why I said it is counterintuitive is that when you do a defrost, the freezer temperature is rising, and then again you have to supply energy to cool it down. So you have to heat the thing in order for the cooling to continue. So it continues in a vicious cycle, basically, right? And another effect of this electric defrost is that because of the significant fluctuation in the freezer temperature, it affects the quality of the products inside as well. If you have some ice creams and things like that, they don't like this temperature fluctuation, right? And then that is another effect of electric defrost. And one last effect is that these defrost heating rods themselves can get above 100 degrees centigrade. So when this melted water is falling on these defrost rods, these heater rods, they will become steam. Once they become steam, they will become water vapor inside the inside the freezer compartment, and again they will form frost. So again, the problem is we are not getting rid of the problem, rather it just circulates inside. Okay? So now, you may not think this is a big problem, but then the global cost of defrosting is 1.6 billion pounds a year, right? Because of the inefficient way in which we put heat into the freezer, and the energy that we have to supply to do it, and then the energy we have to do to cool it down back again is enormous. And considering the scale of refrigeration systems we have, this is the cost of doing defrost per year. So how can we come up with an alternative solution? So if you look at this graph, this is the evaporator temperature during a defrost. So this is a 25-minute defrost, right? You can see that from minus 24, the evaporator temperature is rising all the way to 50 degrees C. And you can imagine the amount of waste heat it is going to put into the freezer when it is doing that. And the green line is what I would call as an ideal defrost, where the evaporator is just above 0 so that it just melts the ice without putting much heat into the freezer environment. So how do we achieve that? So that is what we did in Frigesco Ltd in UK. So I was part of the development team which developed a new defrost technology which consumes no external energy at all. So it virtually runs cost-free. And then it has significant other benefits as well. So we will see how it is done. So if you look at this refrigeration cycle, you have got warm liquid coming out of the condenser, right? And that warm liquid has some sensible heat present associated with it. So we use that, and we use that heat to store the heat in a heat store. So basically, we put a heat store between the condenser and the expansion valve, and the warm liquid is circulated through the heat store. So the heat store will trap all the heat that is available with the warm liquid and store it. So the basic concept is that within the system, we store the heat and then use it during a defrost. So there is no external energy or an external cost of doing a defrost at all, right? So this heat store is basically another heat exchanger, a fin and coil heat exchanger like I showed before, and it is immersed in what is called as a phase change wax. So when this warm liquid is running through this heat exchanger, it will melt the wax, right? And when a defrost is called, when it wants to release the energy, the wax will freeze, and then it will release the energy. So this is the concept of a heat store. The main challenge, you will have to do some modifications to the refrigeration circuit in this case. For example, you add 3 different valves. This valve 1, 2, and 3. So this 3 is a bypass line which will be closed during the refrigeration cycle. So this is the normal refrigeration cycle, wherein this heat store is collecting heat and storing heat, like how your mobile phone is charging. It is collecting heat and storing it. Now when a defrost is called, what happens is this valves 1 and 2 would be closed and valve 3 would be open. So this is what you would call as a defrost circuit, right? So now our aim is to carry all the heat that is present in the heat store to the evaporator and melt the ice there, right? So how it happens is, there is some refrigerant present inside the heat store, and this heat store is at a relatively high temperature, right? And this evaporator is at a low temperature, like minus sub-zero, right? So the refrigerant boils in the heat store, goes up as vapor, condenses here, comes out as liquid, and again boils here. So like that, it keeps on continuing. So this is what is called as a two-phase thermosiphon, multi-phase thermosiphon, because the refrigerant is boiling from the heat store and again condensing in the evaporator. So this cycle would continue until the heat store and the evaporator reach the same temperature. And the heat store is never higher than maybe 20 or 25 degrees C. And that is the limit of the temperature that the evaporator would also get. It won't reach to 45 or 50 degrees, ridiculously high temperatures like that. And above all, it is cost-free. You are not giving external energy. You are just using the system energy. You are storing it and then releasing it on demand, right? So this is a example of what I would call as Occam's razor. There is a principle called Occam's razor, where of all the solutions available, the simplest one is the most effective. So this is a simple solution, but then I think this is very effective, far effective than putting raw heat into the system. So midway through the defrost, what happens is this evaporator temperature slowly starts rising, this heat store temperature slowly starts decreasing, and they will try to attain equilibrium, and the frost starts melting in the evaporator. In contrast to an electric defrost, where you have heaters on the side of the evaporator, and then you release heat from the side, and the heat goes in all directions. Whereas here, the heat is coming from the center. The heat is coming from the condensation of the refrigerant inside the evaporator. So the heat is going from the center. So there is no wastage to the freezer space. So that's a very efficient way of doing the defrost as well, heat transfer as well. So as a result, this defrost cycle is significantly takes less time than the electric defrost. While an electric defrost takes 25 minutes or sometimes 45 minutes in a commercial freezer, this takes only hardly 15 minutes, right? So you are saving energy, you are doing defrost at less time, and the time saved in a defrost cycle is actually energy saved, because if you spend too much time on defrost, the refrigeration is not working during the defrost cycle. So the temperature is rising. So you want to minimize the defrost cycle as well. So next time you walk into a supermarket, you see the chiller cabinet, and you can see a small controller. If you see the letters DEF or DEF, that means that it is undergoing defrost. So usually that will be the point when the chiller cabinet would be at its warmest. So in between, it has to do defrost. Otherwise, it cannot get rid of the frost. We developed this defrost cycle from the scratch, and then we made the prototype. We tested it in the laboratory. We tested it in different actual in situ in different supermarkets and commercial places, and then it showed us good results. There was a savings of 80%. There was a saving of 20% in the total refrigeration cost itself, because you are not supplying energy during the defrost. Also, you are not putting any excessive heat, which means excessive load for the refrigeration. Right? So there was a 20% reduction in the total running cost of the refrigerators. And then your defrost energy was down to 5%. This small 5% is because you are supplying heat to the evaporator. There is condensation happening in the evaporator during a flash defrost. But then when the melted water is falling onto the drain tray, sometimes it refreezes because the water is still very cold. So you have to supply a bit of heat for the tray so that the tray is above zero, and then the water drains off smoothly. So this 5% of small cost is only for heating up the drain tray. Right? And then the defrost time was reduced by 35%. So all in all, as I said, this is the electric defrost, this is the ideal defrost, and you can see how the Frigesco defrost matches closely with that. It's not rising the temperature of the evaporator more than 5 degree or 6 degree, and then you get it done in a very, very short time. Right? And this is the fluctuation of the product temperature. So for example, we kept some packs, specialized packs inside that, and that would mimic the product, for example, the meat product or the ice cream product, and then we would measure the temperature fluctuation during a day. So in the electric defrost, you can see that the blue line, it is fluctuating a lot. Okay, that affects the product quality. Okay, sometimes if you see your if your ice cream has frost in it on the top, you might have seen your ice cream having frost on top of it. That's all because of this kind of issues, the defrost issues, right? It affects the product quality. Whereas for the Frigesco, you can see that the temperature fluctuation is limited to plus or minus 1 degree, right? So all these benefits come, and you can potentially make 1.5 billion pounds in savings and in the refrigeration cost. So this I wanted to share you because just to show to the students that how, irrespective of which technological field you are in, if you want to mitigate the pressures that we put on the environment, because that will attain top priority. It has started attaining priority, but in the next 20-25 years, it's going to attain even more importance, right? So that is where we will be solving the problems, yeah, reducing the energy consumption, going for energy efficient practices, all these kind of technologies in any field you can achieve if you want to achieve these kind of efficient technologies, right? Thank you for your attention.